Hello, everyone. My name is Javier Avesillas, and in this tutorial, I will present a welded T-joint that is simulated using the IGL-GFEM algorithm with a solid-solid coupling between the global and mesoscale problem. The geometry and dimensions of the structure are illustrated in the following figure. And the material properties are Young modulus equals to 2.9 times 10 to the 4 KSI and Poisson ratio equals 2.3. The local features to be modeled for the case of the solid-solid coupling simulation are the fillet welds and the half circle crack, which is located here. The plates are connected only through the welds, so there is a zero thickness seam at the interface between the two plates, as we can see here. As for boundary conditions, the left and right boundaries of the T-joint are fixed in all directions, and the front and back edges are assigned symmetry boundary conditions. Finally, the top surface of the vertical plate has a uniform traction of 5 KSI. To summarize, a graphic illustration of this problem is presented in the following figure. On the left, we have the global model where we model only the two plates. At the middle, we have the mesoscale model. And finally, at the right, we have the local problem. So let's continue with the model generation for the solid-solid coupling scheme. So first, let's open Abaqus. Let's set the work directory. So at this point, we are ready to create the geometry of the global problem. We have several options. We can create the geometry using the available tools, or we can create the geometry using a CAD software and then import the geometry into Abaqus. So I already went through this process, so I'm going to open the geometry. This is the geometry of the global problem. So let's follow the tutorial. We have to set the properties, the assembly, and the step. Let's go to property, create material. Let's use mat 1, mechanical, elasticity, elastic, Young modulus, Poisson ratio, and click OK. Then click on create section. This is a solid section, homogeneous, continue, and then click OK. Finally, we have to assign the section. Sometimes we would like to avoid the creation of unnecessary sets. So if possible, uncheck this option. Select the whole model and click done. We're going to use our solid section and mat 1 as the material. Click OK. Now let's create the assembly. Create instance, part global solid, OK. Now let's go to the step module, create a step, Let's use the default values, insert new step after initial, and we're going to use a static general. Continue. Let's use the default options and click OK. Then in the load module, we have to specify the boundary conditions. So we have boundary conditions, create boundary condition. Let's specify the left side of the T-joint, mechanical displacement rotation, continue. And now we select the left edge, click done, and fix all the degrees of freedom. Repeat the process for the right edge, mechanical displacement rotation. Done. Fix the 3 DOFs and click OK. Now we have to assign the symmetry boundary conditions. Let's create a new boundary condition. Front, mechanical displacement rotation, continue. We have to select all the surfaces. Click done. And in this case, the symmetry boundary condition is equivalent to fixing the U3 DOF. Click OK. Repeat the process for the back surface. Create boundary condition. Display mechanical displacement rotation. Continue. Let's select all the surfaces. Click done and fix U3. Finally, let's prescribe the applied traction. Let's go to create load, pressure, continue. Let's select the top surface, click done, and the magnitude is -5. Click OK, and we have our prescribed traction. As you can see, the model that we have is similar to this one. Now let's go to the mesh module. And at this point, it is important to know that the user must guarantee conforming meshes at the global mesoscale interface. So let's go to the mesh module. Let's create our mesh. So first, let's define the element type. Click on Assign Element Type. Select the region, select the whole model, click Done, and just make sure that Reduce Integration is unchecked. And we are using a C3D8 element, which is a 8-node linear brick. Click OK. Done. Now let's check if our mesh matches the mesh of the tutorial. So we can see that we have 3 elements through the thickness. So let's specify three elements through the thickness. Let's delete all the previous seeds just in case. Okay, now we specify 3 elements through the thickness. Click done. Method by number 3. Number of elements equals to 3 and click OK. Now we have 9 elements along this edge, the same here and here. So select the edges. We have selected all the edges. Click done. And let's use 9. Click OK. Now we have 36 elements along this edge, the same here and here. So let's select those edges. And specify 36. Click OK. Finally, we have 30 elements along this edge. So let's select those edges. Click done. And select 30. Click OK. And now let's mesh the part. Click yes. Let's show the mesh. And our mesh is ready. The next step after we created the mesh is to go back to the assembly module and first select all the global elements that are at the global meso interface, but inside the mesoscale region, and create an element set with the name loc interface element. So let's do that. Let's go back to the assembly module. Let's show the mesh. And let's create an element set. Tools, set, create element. Let's use the name loc interface element. Click continue. And now we have to select all these elements that meet the previously mentioned criteria. As you can see, we have selected all those elements, and let's click done. Now we have to select all the global nodes that lie at the global meso interface and create a node set with the name loc interface node. Let's go back. Tools, set, create node with the name loc interface node. Continue. And let's select all those nodes that meet the previously mentioned criteria. And click done. Finally, let's go to the job module, create a new job, then perform a sanity check, and then finally write the input file for the global model. So let's go to the job module, create a new job. Let's use the name global solid. Click continue. Okay. And then we go to the left menu, right click on the job name and click on data check. The data check is finished, and we got the message saying that everything is fine. The data check completed successfully. So now we can right-click on the job name and click on Write Input. And the job input file has been written to this file. And here we have the input file with all the information of the global solid model. Now let's continue with the mesoscale model. So again, let's open Abaqus. Let's set the work directory. And in the part module, define the geometry of the mesoscale model. Once again, we can use the Abaqus available tools, or we can create the geometry using a CAD software and then import the geometry into Abaqus. So I already did it. So let's open the geometry. And this is the geometry of the mesoscale problem. So one important thing is that, again, the user must guarantee that we have a conforming interface at the meso global region, as you can see in this picture. So let's continue. Let's go to property, create material, mat 1, mechanical elasticity, elastic, yaw modulus, Poisson ratio. Click OK. Let's create a section. It's a solid section. Continue. Let's assign the section. So uncheck this box and select the whole mesoscale model. Click Done. Solid material 1. OK. Then go to Assembly. Create instance. And we're going to use the mesosolid. Click OK. Now let's go to a step. Create a step. Insert the new step after initial and static general. Continue. Let's use the default values and click OK. Now, in this case, the vertical and horizontal plate are connected through the welds only. So there is a 0 thickness seam along this region. So let's create the seam. In this case, let's go to interaction, special, crack, assign seam. No, this is not. Special, crack, assign seam. And this is the seam. Click Done. We got a message saying that the selected instance is a dependent instance. So let's go back to assembly instance, right click, and let's make independent. And now repeat the process. Interaction, special, crack, assign seam. Done. We are ready, and we can continue with the following step. Now we have to specify the boundary conditions. So the mesoscale problem doesn't have any boundary conditions, any special boundary conditions, because all the applied displacements at the global meso interface will come from the solution of the global problem. But in this case, the mesoscale problem inherits some boundary conditions from the global problem, which are the symmetry boundary conditions at the front and back surfaces. So in ISET, we prescribe surface boundary conditions, but in this case, we do not have surface boundary conditions in Abaqus. So a quick workaround that we can do is use a dummy pressure to get the surface IDs, and then use the surface IDs to specify the surface boundary conditions in ISET. So let's do that. And that process is described here. So it says apply a dummy pressure load using these names. And then we need some user intervention to specify the actual surface boundary condition that we want. So let's create this dummy pressure, create load, pressure, and let's call it surf PC1. Continue. Let's create a surface in this case, and let's use the same name. And select the surfaces. Click done, and then specify a magnitude. Click OK, and repeat the same process for the back surface. Create load. Let's use surf BC2, pressure, continue. Surf BC2, and select all the surfaces. And click done. Let's use a magnitude of 10 to the negative 10. Click OK. Let's continue with the tutorial. Now we have to mesh the mesoscale model. So let's go back to Abaqus. Let's go to the mesh module. And first, let's assign the element type. Let's select the whole model, click done, and just double check that reduce integration is not selected and we are using linear geometric order. So we will use C3 D8 elements, which is a 8th node linear brick. Click OK. And now we have to seed the edges to get the same mesh as in the tutorial. So as we can see, we have 3 elements through the thickness. So let's mesh this model. Let's select these edges. Click done by number, and let's use 3. Click OK. Now we have 1, 2, 3, 4, 5, 6 elements along this edge here and this one. So let's select those edges. And specify 6 elements. Click OK. Now we have 3 elements here, here, the same in these edges. So let's select these edges. Click Done and specify 3. Click OK. We have 4 elements along this edge. Let's select the edges and use 4. Finally, we have 30 elements along this direction. So let's select all those edges. Click Done and use 30. Click OK. Now we are ready to mesh the part. Click Yes. And this is the mesh that we have. As you can see, it's the same mesh as in the tutorial. So the next step is go back to the assembly module and select all the mesoscale elements that are at the global meso interface and create an element set with the name glove interface element. Let's do it. Let's go back to the assembly module, tools, set, create. This is an element set with this name. Continue. And let's select all these elements. Click Done. And then select all the mesoscale nodes that lie at the global meso interface and create a node set with the name glove interface node. So again, let's go to tools, set, create, node, and use this name. Continue and select all the nodes and click Done. Now we have to create a new job and do a data check and finally write the input file. So let's go back to Abaqus. Let's go to job, create job, meso solid, continue, click OK. On the left menu, right click on the job name and click on data check. So the data check has completed successfully. So we can right click on the job name and click on write input. And the job input file has been written to this IMP file, which is located in our work directory and has all the information for the mesoscale problem. Finally, to create the local model, in an IGL-GFEM GL simulation, the local model is created automatically, and it is defined by the set of mesoscale elements that lie inside a user-defined bounding box. As a second option, the user could also create the local model using Abaqus, following the same guidelines as for the mesoscale model. But in this case, the user must guarantee that the local mesh is nested in the mesoscale mesh. So let's continue with our IGL-GFEM GL simulation with solid-solid coupling between the global and mesoscale problem. And now let's do the Abaqus to ISET conversion. The steps to convert an Abaqus input file into ISET format are the following. First, if the Abaqus input file was generated in Windows, we recommend copy and paste the content of the input file to a new file with the same extension .imp. This is needed to delete any special character that might have been generated and might cause troubles during the conversion. So I already did it. This is the original global solid input file, and I created a new file where I copy and pasted the content of the original file. And I repeated the process with the mesosolid.imp. So now let's convert our global model. The next step is to verify that the Abaqus to ISET converter and the Abaqus input file are located in the same directory. So both files are here. Now let's open a terminal window and execute the converter. Let's follow the instructions. So our global model is made of hex 8 elements. So we have to choose option 3 and then provide the name of the input file. And then press enter. So if there are no errors, we get this message indicating that everything is done. And then 2 files are generated. This file with extension .grf, which is the solid global model in ISET format, and this one IGL.imp, which is a clean version of the Abaqus solid input file. Let's rename this GRF file with global mesh. And let's rename this file with first example block. And now let's repeat the process with the mesoscale mesh. So both files are in the same directory. Let's open a terminal window, execute the converter, and follow the instructions. So again, our mesoscale model was made of hex 8 elements. So we have to choose option 3 and then provide the name of the input file and press enter. There are no errors, everything is correct, and 2 files are generated. The file with extension GRF is the mesoscale solid model in ISET format, and this one is a clean version of the Abaqus mesoscale solid input file. Let's rename this file as mesomesh. And since we are not going to run the mesoscale model in Abaqus, we can leave this file as it is. The next step is to do the node equivalence. During an IGL-GFEM GL simulation, there is an interchange of nodal information between the global and mesoscale model along the global meso interface. So for the case of a solid-solid coupling scheme, we need to generate a one-to-one map between the global and mesoscale nodes. So the steps to generate this node equivalence between the 2 models are: first, verify that the Abaqus to ISET converter and the Abaqus global and mesoscale input files are located in the same directory. Open a terminal window, execute the converter, and follow the instructions. So all the files are here. Let's open a terminal window
execute the converter and follow the instructions. In this case, we are doing a solid-solid coupling, so we have to choose option 10. Provide the name of the input files, global solid, the name of the mesoscale file, and press enter. The processor is done, no errors, and the following files are generated. First, we have this interface resforce.lod. This file contains concentrated forces applied at the interface nodes of the global model. As a side note, this file is used only when the global problem is solved using Abaqus, and it has the following format: global node ID, DOF, and the value. Global node ID, DOF, and value. And the other two files are node equiv append to global. And this file contains the node equivalence information in the following format. So for a solid-solid global mesocoupling scheme, this is the format of the file. And finally, we have this node equiv append to lock, which has the node equivalence information in the following format. Again, for a solid-solid coupling scheme, this is the format. Finally, depending on the type of IGL-GFEM simulation, the content of these last two files should be used as follows. For an IGL-GFEM simulation where both global and mesoscale models are solved using ISET, we have to open node equiv append to glob and append its content to the end of the converted global model in GRF format. So let's do it. Let's open node equiv append to glob and copy all the content to the converted global mesh. And then click on save. Then open node equiv append to lock and append its content to the end of the converted mesoscale model in GRF format. And then click on save. And this is the end of the node equivalence process. However, there are some other steps that we need to do. For instance, we need to include some boundary conditions in the meso-mesh model that will be used for the local problem. So let's open again the meso-mesh. And copy these boundary conditions. And click on save. Finally, let's recall that our solid-solid coupling scheme has a mesoscale model that inherits some boundary conditions from the global problem. And we are planning to prescribe surface boundary conditions. So we had a workaround to create the surface boundary conditions. We previously applied a dummy pressure at the surfaces where we are planning to apply these surface boundary conditions. So we have to open this file again. And first we have to delete these dummy tractions or pressures. So let's delete these ones. And then go to begin boundary and copy and paste these surface displacement boundary conditions. This will be used for the front surface and this one for the back surface. So front surface was number 1 and back surface was number 2. And the components are 0, but only U3 is fixed. And then click on save. Let's continue with the IGL-GFEM simulation files for a solid-solid coupling between the global and mesoscale problem. So the following file names are suggested and are the ones used in this tutorial. However, other file names can be used by changing the input file names in the TCL files and Python scripts. For the case of an ISET simulation, running an IGL-GFEM simulation where both global and mesoscale models are solved using ISET requires 5 files. The file IGL simulation.tcl, which is the simulation driver. We need IGL simulation glob.tcl, which runs the global model. We need global mesh.grf, which in this case is the global solid model in ISET format, and this was supplied by the converter. We need mesomesh.grf, which is the mesoscale solid model in ISET format. Again, this was supplied by the converter. And if we are solving a fracture problem, we need a crack.crf, which is the crack surface representation in ISET format. As I mentioned before, these are the files that we need. Some of these files may need modification before running an IGL-GFEM simulation. So first, IGL simulation.tcl, we can modify different parameters such as the number of IGL iterations, the polynomial order, the bounding box coordinate used to define the local problem, etc. So let's open this file. And here we can modify some input parameters. We may need to modify IGL simulation glob.tcl because here we use a bounding box to define the global meso interface, as you can see here. Then we may need to modify global mesh.grf because, as stated in previous sections, the node equivalence must be appended to the end of this GRF file. So let's open global mesh. This is a solid global mesh made of hex 8 elements, and the node equivalence is already here because we did it in a previous step. Again, we may need to modify mesomesh.grf to include the node equivalence and also include the boundary conditions for the local problem. So let's check this file, mesomesh. This mesomesh is also made of hex 8 solid elements. The node equivalence is already here because we did it in a previous step. And the boundary conditions for the local problem are already here because we also did it in a previous step. So now let's continue with an Abaqus ISET simulation. The steps outlined here are for running Abaqus in a remote machine or simply in another folder of the same machine. Running an Abaqus ISET IGL-GFEM simulation where the global model is solved using Abaqus, while the mesoscale model is solved using ISET, requires 10 files in the directory where the Abaqus global model is run, and 4 files in the directory where the ISET mesoscale model is run. So in the folder where ISET will be run, we need IGL simulation.tcl, which drives the whole simulation. We need the mesomesh.grf, which is the mesoscale solid mesh in ISET format. Again, this file was supplied by the converter. If we are solving a fracture problem, we need a crack.crf file, which is the crack surface representation in ISET format. And we need this ISET to abaqus.py, which is a Python script that converts interface residual forces from ISET format to Abaqus format. So these are the files that we need. Then in the folder where Abaqus will be run, these are the files that we need. This is the Abaqus global model. This is the interface residual force. And there are some other scripts that are needed to run the global problem. These are all located in this folder where Abaqus will be run. Again, some of these files may need modification before running the IGL-GFEM simulation. For instance, in this case, we need to modify IGL simulation.tcl, and we need to provide some information about the machine where we will run Abaqus. For instance, in my case, I need to provide the address of the workstation, my password, and the path where my folder will be located. We can also specify the name of the input files, the polynomial order, number of iterations, tolerance, coordinates of the bounding box to create the local problem, etc. Again, we may need to modify mesh.grf to include the node equivalence and also to include these boundary conditions for the local problem. So let's check. The boundary conditions for the local problem are here. And the node equivalence is already here because we did both additions in a previous step. And this concludes this step. Let's continue with the solution of the T-joint using IGL-GFEM with solid-solid coupling. First, let's use the ISET simulation. It is worth noting that we will use an staggered algorithm, which is presented in this section. First, we will have to create a folder with this name and copy all the necessary files that we need to run an IGL-GFEM simulation with ISET coupling and that were described in this section, and also create a symbolic link to the ISET executable. I already did it. I have all the necessary files here and also an ISET executable. Now open this file and check that you are using the same input parameters. The approximation space is 2 for both models. This is the number of IGL iterations. This is the tolerance value. And this is the number of global-local iterations. So let's open this file. We are using 2 as the polynomial order, maximum number of iterations, global-local iterations 1, correct? maximum number of IGL iterations, 30, correct. Tolerance is correct. So everything is in place. Let's close this file. And now solve the problem with ISET using the following command. So let's open the folder. Let's open a terminal window and execute this command. What we are doing is basically running this TCL file and saving all the output data in this file. Press enter. Now we are running the IGL-GFEM simulation. So once the simulation is done, we have generated several files, as you can see here. But the following 5 files are particularly useful to us to check if everything went okay. The first one is out.txt, and this file contains the norm of the residual forces at the global meso interface. We need IGL simulation.cm SIF, which contains the stress intensity factors along the crack front. This file, IGL simulation glob.btu, contains the global solution. IGL simulation iteration 1 eg.btu contains the solution of the enriched mesoscale problem. And this file, IGL simulation iteration 1 local, contains the solution of the local problem. So first, to check if everything is correct, let's open out.txt and search for relative norm residual. We will have to search for this value and plot the value in the y coordinate and the iteration number in the x coordinate. And you should get a plot similar to this one. Now let's check the deformed configuration of the global problem. So let's open ParaView and open this file and perform a warp by vector with a scale factor of 10. And then you should get a deformed configuration similar to this with similar values in the y solution. I already did it. And as you can see, the deformed configuration looks pretty similar. And also the values are similar. So I will have to increase the number of decimal places, but seems like everything is fine. Then you could also check the von Mises stress in the enriched mesoscale problem. And then you will have to perform a slice with origin at 0, 0, 15 and C normal. So basically, if you follow all these instructions, you should get something like this. So I already did it. And as you can see, we have a stress concentration at the crack tip, which is also observed here. Finally, if you follow again all these instructions, which is basically telling you to plot the stress intensity factors along the crack front, you should get these plots. And the stress intensity factors are located in this file. So you will have to plot K1, K2, and K3 in the y coordinate and the coordinate of the, the angle with respect to the center of the crack in the x-axis. And you should get a plot similar to this. And in this way, you can check if your simulation is correct. Now let's continue with the second part of the solution of the T-joint using IGL-GFEM with solid-solid coupling. In this case, we will use an Abaqus ISET simulation. So let's scroll down. And this is the Abaqus ISET simulation. So in this simulation, we will use a stagger scheme, which is presented in algorithm 10.1.2. First, we will have to navigate to the folder where Abaqus will run and check that all the necessary files described in this section are present. So since I will be running Abaqus in the workstation, I already did it. And this is my workstation folder, and I have all the necessary files here. Then let's create this folder and copy all the necessary files that we need to run an IGL-GFEM simulation with Abaqus ISET coupling described in this section. And also copy a symbolic link to the ISET executable. Again, I already did it. I created this folder in my local machine, and I copy and pasted all the necessary files to run the simulation and the ISET executable. Finally, let's check if we are using the same input parameters. Approximation space of both models equals to 2, 30 IGL iterations as maximum. This is the tolerance value, and maximum number of global-local iterations equals 1. So let's go back to the folder. Let's open IGL simulation.tcl. And we are using 2 as the polynomial order, 1 global-local iteration, 30 as the maximum number of IGL iterations. We have the correct value for the tolerance, so we are ready. Then solve the problem with ISET using the following command. So we will have to copy this command, go back to the folder in our local machine where we will run ISET. Let's open a terminal window and execute this command. And then we will be running the IGL-GFEM simulation using Abaqus ISET. I already did it, so the simulation is done. As you can see, I also copied the file from the workstation, because besides the original files that we need to run the simulation, Abaqus also generates some useful information. However, now let's proceed with the tutorial. So ISET generates several files during its execution. However, the files that are particularly useful to us is out.txt, which contains the norm of the residual forces at the global meso interface, IGL simulation.cm-SIF, which contains the stress intensity factors along the crack front, IGL simulation iter1-EG, which is the deformed configuration of the enriched mesoscale problem, and IGL simulation iteration1 log, which has the local problem solution. In this case, we do not have a solution of the global problem because we haven't implemented a translation between the Abaqus output file to Paraview format. So we will have to use a workaround to see the solution of the global problem, and that will be presented in a different video. So now let's use a text editor to open this file out.txt and search for relative norm residual. And we will have to plot this value in the y coordinate and the iteration number in the x coordinate. And then we will have to check that we have the same plot. As I mentioned before, we will have to use a workaround to get the deformed configuration of the global problem, but that will be presented in a future video. Now let's post-process the IGL-GFEM solution using ParaView of the enriched mesoscale problem. So if you follow all these instructions, you should get the deformed configuration of the mesoscale problem. I already did it. And as you can see, we have a deformed configuration, which is quite similar to the one in the tutorial. And also the values are very close to the one in the tutorial. So it seems like everything is correct. And then we will have to follow these instructions to show the von Mises stress at the enriched mesoscale problem. So if you follow these instructions, you should get the von Mises stress in the enriched mesoscale problem. And as you can see, we have stress concentrations near the crack tip and here, which coincides with what is shown in the tutorial. Finally, we will have to go back to the folder and open the stress intensity factors file, which is this one, the one with extension SIF. And we will have to plot the stress intensity factors in the y coordinates. And we should get something similar to this plot. So if your results match with the ones presented in this tutorial, your IGL-GFEM simulation is correct. Let's go through the Abaqus global model post-processing for the case of a IGL-GFEM simulation with solid-solid coupling between the global and mesoscale problem. So if an IGL-GFEM simulation uses Abaqus to solve the global model, there is no conversion of the abaqus.odb file to ParaView format. So in order to visualize the solution of the global model, we need to use a modified version of the abaqus.imp and the final version of the interface res_force.lod. The process is detailed as follows. So first, create a copy of the Abaqus global model file, which was used in the IGL-GFEM simulation. Rename this file as IGL simulation glob post.imp. So let's go to the folder. For the solid case, this was the original file that I used in the IGL-GFEM simulation. And this is the last version of the interface residual force. So let's create a copy of this file. And let's rename the file. Okay, then the next step is use a text editor to open this file. Search for include input interface res_force. Delete everything after this line, but excluding nth step, and then copy and paste the following text. So let's copy the text. Let's go back to the folder. Let's open the file. Let's search for include input interface res_force. Delete everything after this line, but excluding nth step, and paste the code that is here. Then save and close. So the idea of this code is to request as output the displacement field and von Mises stress. Please refer to the Abaqus manual if other quantities are needed. So now we have to open Abaqus and set the work directory. Let's set the work directory. Solid, post process global solid. Okay. Now we have to create a new job and specify a job name. And in the source tab, choose input file and select the new file that we just created. So let's go to the job module, create a new job. Let's call it post global solid. Let's choose input file and then select the input file that we just created, this one. Click OK and continue, and click OK. Then on the left menu, let's do a right click on the job name and click submit. So if there are no errors, you should get this message saying that the job has completed successfully. So then right click on the job name and click on results. And now we can use the visualization module to show the deformed configuration. Let's click on plot contours on deformed shape. And let's select the displacement and the Y component. And now let's check if we have the same deformed configuration as in the tutorial. So let's scroll down. And this is what we have in the tutorial. The deformed configuration looks similar, and the maximum U2 displacement is 5.1 times 10 to the negative 1, which is the same value that we have here. So in this way, we can check that the Abaqus global model is correct.